Hi everyone. Today we're going to talk about a war story that we read on the Algorithm Design Manual by Skienna. The war story we've chosen to tackle is The Mystery of Pyramids because of its interesting nature of problem, and let's face it, we thought the name was pretty cool. Apparently, someone needed Stephen's help on the design of an algorithm. They specifically said to him that we want to use a parallel supercomputer for a numerical calculation up to 1 billion, but we need a faster algorithm to do it. So basically, they had some problem, they found an algorithm, but it wasn't efficient enough for their 1 billion computations, and their computer stopped the work before it was meant to. First, let us describe the problem. Ever heard of the Waring's problem? Probably not, but don't worry, we're here for you. The Waring's problem is a problem in number theory that asks whether every integer can be expressed at least one way as the sum of at most 4 integer squares. For example, 78 amongst other can be expressed such as 7 squared plus 5 squared plus 2 squared. Now this is a solved problem from 200 years ago, but we wanted to solve another version of it. We introduced pyramidal number, which can be expressed with the formula on the table. For example, for m equals to 2, we get 2 to the third minus 2, which is 6, which then we divide by 6 and get the number 1. So 1 is a pyramidal number, and so is 4, 10, 20, etc. Now we want to prove that every integer can be represented by the sum of at most 5 such pyramidal numbers on all numbers from 1 to 1 billion, and we want to do that by using a supercomputer. Remember when we said that there was an already constructed algorithm for this problem, but it wasn't efficient enough? Well, now we will present that. The guy who came for help had created an array that stored all the pyramidal numbers from 1 to n inclusive. The array looked something like that, presented on the board. The complexity of this array would be theta n to the power of 1/3. To test each number k in this range, he did a brute force test to check whether it was the sum of 2 pyramidal numbers. If not, then check for 3 of them, then 4, and finally 5, until it first got an answer. The total time spent was O(n) squared. And notice that we put a little red flag there? Well, that's to warn us that the complexity is not good at all and it won't perform well while being executed.
How do we fix it? Well, Stephen came up with some striking ideas. He used 3 main ideas to better the performance and hopefully reduce the time complexity, which were the knapsack problem, the two-table, and binary search. The knapsack problem is a problem in combinatorial optimization. Given a set of items, each with a weight and a value, determine the number of each item to include in a collection so that the total weight is less than or equal to a given limit and the total value is as large as possible. We used it because for each value of k, we were seeking the smallest set of pyramidal numbers that add up to exactly k. In our case, the weights are the pyramidal numbers no greater than n. With an additional constraint, the knapsack holds exactly k items. A standard approach to solving knapsack calculates the sum of smaller subsets of the items for use in computing larger subsets. In order to implement this, we now use the second idea that Stephen came up with. The two-table. The two-table is going to be a sorted array. Its elements will represent all the possible different sums of every pair of numbers in the array of the pyramidal numbers from 1 up to 1 billion. In fact, there are only 1,816 pyramidal numbers, therefore there will be at most 8,816 squared in the two-table. But after eliminating duplicates, there will only be left about half of them. At this point, if we want to find the combination of pyramidal numbers for a given number k, we can first check if the number is pyramidal. Check if the number is in the two-table. Check if k minus p of I is in the two-table, where p of I represents the array of the pyramidal numbers. Check if k minus t of I is in the two-table, where t of I represents the two-table itself. Notice that we won't check for the sum of five pyramidal numbers, because there are only 241 known numbers up until a billion that need to be represented by five pyramidal numbers. We can leave those numbers aside from the beginning. To make our job easier and the time complexity better, whenever we check for a value in the to table, we will use binary search. After some other improvements, such as replacing binary search with interpolation search and using hash tables instead of arrays, we will get a time complexity of big O n to the power of 4 over 3 log n, which is clearly way better than big O n squared. The moral of this war story was to see how a potential algorithmic speedup is much more valuable versus expensive hardware that still won't fix our problem. We hope you liked it.